let's switch to the bench. Let's enable the audio and let's wait until the audio is there before we can start. We don't see my laptop for now. Yep. And the audio should arrive. Yep, it is there. Everything is working, so let's start the stream. Well, today I received the next boards. You might know that I built a lot of cable testers. I built the micro USB cable tester, the USB-C cable tester. I even made videos quite recently to present them. I already had them in my shop, but I didn't have any proper video presenting them. And now I did videos, so if you're following my blog, you will probably have seen the video. There will be one coming the next day also. But so we did USB-A to micro B. We did USB-C to USB-C, and now, because there's still a transition phase, I decided to make USB-A to USB-C cables, because there too you can have different things. And I think this is my second prototype. Do I have one? Yep. What is this? Oh, let me get it. Here. Let's zoom a tiny bit more. Here is my first prototype. It used a through-hole USB-C because I still had them. USB-C, USB Type A, because I still had them. I even built a prototype and half through-hole USB-C. Now on the new one, both of the things are SMD. This one will be a bit trickier to solder. Let's see how we'll do it. This one, so this is version 0. Yep. Here we see this is version 0, and it had a couple of issues. Some cables are not using all the V bus are not connecting to all the pins. So if you see on the USB-A to USB-C cable, so on the USB-C you have 4 V bus and 4 ground pins, because you need to handle a lot of current. The problem is that, and because it's reversible. Now, some cables actually don't use all the 4 pins, although there is only one wire. No matter what happens, there will be only one wire in the cable. But actually, I found some cables which don't use all 4 pins. And I didn't rely on having 4 pins there, just on one of the pairs being available, or 2 of them, 1 or 2 of them. So some cables didn't detect the power. That was the first issue. The second issue was about the shielding. On some cables where I know there was no shielding, it was detected as shielded. This has to do because I was powering up the shield. So the LED goes through the shield, and then if the shield is grounded, then it's okay. The problem is that, now in USB-C cables, shield is grounded within the plug of the cable. So if shield is grounded within the plug of the cable, I could be a false positive, because I don't actually test if the shield goes from one end to the other. So I fixed that using 2 transistors. This is also the demo you see here. So yeah, this was my first version. Here you see a small demo, and this was got a sort of hack to actually implement this correct shielding detection. And this is when I ordered the second version. And today we will test the second version. We will assemble it and test if it works with all the AC cables I have. So here we have the boards, and let's assemble one of them. I think we will start with assembling the USB-C connector, because this is the hardest one and it's only SMD. I haven't used them. I switched to them because the through-hole connector I had very poor yielding. and that wasn't good. And using the SMD, the yield is quite good, but it's harder to solder. So let's have a look at the book, and here, yeah, I ordered some of these USB receptacles in SMD only. So you can solder them using a soldering iron because the pads are below. And I don't have, I can't solder them using stencil because I didn't order a stencil with it. But we will still solder it using hot air. Maybe a heating plate also that could help. I will probably use a heating plate. So what we'll do is heat up and down from both sides, and then put the USB-C connector on it. And here is my heating plate, and it's around 200 degrees, and it's completely not temperature regulated, but it somehow self-regulates up to 200. The problem is that, yeah, how can I switch it? This is getting warm, and also the feet are getting warm, and if I leave it here, I will have some burn marks on there because there is no isolation. So what we will do is we will use this pizza plate, and we will do work on the pizza plate. That's the pizza plate. Up, and this will isolate from the heat for sure. There is no issue. So let's plug this in. Let's switch this on. I hear it buzzing, so it means it works. We'll have one plate. Ah, there is a chip over here. So let it get warm. Problem is I won't be able to actually test if it's soldered or not correctly, or hardly test it. We'll just have to. What was that? It made a big flop, but no, power is still going through. Up, we need the soldering iron. Chuck. And we need plenty of flux. And with that, we should be fine. And the hot air up to 400 degrees. Now, let's put the soldering iron is not warm yet. And let's test if it actually fits, because I've never used this part myself. Is there really? Yeah, there is. Yeah, the footprint fits really fine. It is getting toasty, that's good. So let's put a tiny bit of solder. Normally you should put some paste. We can actually put some paste. It's the same thing. Can just put some solder using the soldering iron. Just not too much, like here, we did too much solder. That's still too much. We can put flux on it. Where is my flux? Here. This will help us clean the pads. Yep. And the flux is shiny. Now we can put the thing on top. Oop. We see the flux fuming. And we still need to heat it with the hot air, because I see it's not sticking. So hot air. I hope this will work this way, and the hot air should be set at 400 degrees. It's starting to glue to it. I should have put more solder. Yep, I should have put more solder. Well, let's try if it works. If it doesn't, we still have 4 other boards we can try on. Oh, that seems to be okay. Let's switch this off. Could actually solder everything on the heating plate. Nah. We'll put at least, yeah, there wasn't enough solder. There wasn't enough solder. I think on the bottom it won't have soldered completely fine, but we'll test if it works. It's also a tiny bit melting the plastic. Okay, this is done. Let it cool off and we will solder the remaining parts. Afterwards we can solder the connector. So this needs to cool down. Now, schematic. There are not a lot of parts. There are many LEDs, resistors, and actually 2 transistors, which I need to get. MOSFETs, do I have them here? Yes, and yes. I do have them here. So, I don't know which resistor is what. I need the fabrication diagram. PCB. I can somehow. Most of the things I can guess, but I don't know which transistor is what. Schematic. And you go here. Up. Up. This is the 138. This is this one. Yep. This one here is Q6. 128. That's the most important part. The rest I can figure it out. Is this still warm? No, it's okay. So you also will want to see what I'm doing. Obviously, that's why you're not here. Up, 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 up. So 128. This is an NMOS, right? 128. This is the NMOS. Yeah, I could have guessed it because I see the ground connection. And you use NMOS to switch to ground. Generally, you can also switch high side, but it's a bit more tricky because you need kind of a voltage booster. So how does Aber? Well, you can see from the schematic. I can give you the schematic, so you can actually see how this works. Tack. No, this is the schematic, and this is how the USB-C cable test, USB-AC cable tester works. And actually what I do is I measure if the 2 shields are interconnected and if they're grounded. I do these 2 tests, and I'll tell you why. So this is how it should be in a cable, in a USB-C cable. No matter if it's USB C to C, C to A, and so on. Here in this case it's C to A. But that's not too important. Just USB-C requires you to have the shield grounded. So yeah, As I said, now if there is still a debate, should shield be grounded and how? Well, in USB-C, you already have the answer. In USB-A, you can still choose, and actually on the hub, I still give the option to choose the resistor and the capacitor to kind of control the ground connection and reduce the EMI. In USB-C, that's not the case anymore. It's immediately ground. Okay, normally I think these two have a 100K pull. These are the 200. I think these are the 200Ks. They're still in line, but this is with the LED. Yep, 100K. Here we have 100K. Let's use up to 5%. This is just bias resistor. So if nothing happens, do I still have some of them? Don't remember. I need some leads, some battery holder. Okay, that's one side. That's the other. Ooh, this one isn't really superbly soldered, but we'll fix it. Fixed. Okay. Now, why is it bumpy? It's just, this is bumpy. Yeah, it seems fine. Yeah, exactly. So if you see some cables where the shield is not grounded internally, you can connect the shield to these pads, and these are grounded. I think I have a cable where the shield is not grounded internally. Okay, LED time. Well, first the resistors for the LEDs, and then the LEDs. I think I don't have all the colors here. Maybe I do. Let's see. So RP is using. Where's RP? RP. Why do I have RP going to this? Yes, I'm testing this resistor. But where's the LED? RP. 1K. Yeah, red. It's a red LED. Makes sense. Power. I generally have power LEDs in red. Red 5%, 1K. This is. Damn it. This is 1K. Up. Somehow on this red solder mask, the solder likes to stick on. Still makes solder mask, but it really likes to stick on red. Not sure why. Okay, USB 3. USB 3 should be blue. Oh no, it's green. Why? I wanted it to make symmetrical. So it's the 2.2K. 2.2K, and actually it could be even 4.7K, but for now it's a 2.2K. That's USB 3 tester. Then we have shield. Shield is yellow. Yeah, I don't have yellow here. I need the yellow LED, and it's 470 ohms. 470, and then it should be symmetrical. Okay, that's 470. So USB 2 should also be green. Yes, so it's a 2.2K. Okay. One side. And the other. And the last one is red, so it's 1K. Okay. The 1K are getting empty. I need to get, this is not 1K. Ah, it is 1K, but it's not, it's 1.5K. This is not 1K. You go away. And here we have 1K, not 1%. So the difference is the marking. If you see 102, I mean 1.0 and then 2 times 0. So it's 1000, so it's 1K. And because it's only numerical, so 102, it's a 5% resistor. If it's a 1% resistor, they use letters. And I think it's 01B for 1K. Now the LEDs. We have two red LEDs. These are power, and then we have two green LEDs. These are the USB. One yellow, which I don't have. I will use blue because I have blue here. Oh no, I do have yellow. Okay, I do. Red. Then we have green. The blue, I don't really like the blue. I didn't find any super blue LEDs. So yellow. Up we see the cathode marking with the green on the top. Then we have again green. And red. And now the other side. Okay. This is done. Does it look okay? Yeah, it looks okay. Now we can have the USB-A connector. And this is a USB 3 connector because I also want to test USB 3 cables, which exists. And yep, as I sorted a bit. Oh, this is weird. Here we have two kind of spades, but this is only to hold off. It's not soldered or anything. We just have these two tabs for it to stick. Let's see if it's robust enough. I've never used these connectors yet. I find it a bit flaky and a bit. I doubt tiny bit that this is robust enough, but we'll see. It's not sitting well. And the pads I designed are mainly made for SMD. Okay, now I can solder it correctly. And second tab, flow inside. You have to hold the whole weight. But the tab is long enough. I think it will hold. see it's a bit harder to solder because it's meant for SMD soldering. The tab is ridiculously small, it doesn't go through the board. So I hope that my solder goes down to the tab and holds it. Ooh, yes, I think so. Now this side. Damn it. This is what I didn't want. A solder bridge. I'll need to use the pump. Let's get some solder off. Still too much. Okay, the rest should be fixable with the soldering iron. And the last pin. Doesn't look super nice, but it looks connected. Yep. And the last parts. Coin cell holder. I think they are in this box. Yeah, coin cell holder. So, do I still have some of them? Yeah, I still have a few of them. So, let's put the solder on one tab. Put the coin cell holder on. Doesn't have to be that precise, the pad in the middle is large enough. Okay, that should be it. We'll test if it works. I need a battery. I will use one of my batteries which I have here. And we will test if the USB AC cable tester works. I would like to test if there are shorts in the beginning. So let's go to ohm measurements. And can you see the measurements? No. Okay, I still need to debug this stupid thing. At least it detected inactivity. So that's already something new. What's the resistance? Yeah, that's fine. Okay. So let's put the coin cell and let's get some USB-C cable. I think I have one here, USB-AC, but I have more of them in one of the bags. I think this is only USB 2 and I think this is not shielded. So at least power. Yep. Power RP, this is good. That doesn't have USB 3 and I think it was not shielded. So let's verify it. And to test the shielding, we just measure on both sides, and there should be, nope, yep, there is no shield. See, we are in the mega ohm, so the shield doesn't go through this cable. Although the cable looks nice, can only be used for USB 2. Unshielded USB 2 cables are okay. Not ideal, but they're okay. Now, USB 2 to all and USB 3 cables. USB 3, no, that's AB, that's USB extension, that's USB micro, AB miss cables plus adapters, maybe there. Let me find my cables. I have so many USB-C cables, USB cables in general, because I'm doing a lot of USB-C cable, USB cable tester. So here we have USB-C to everything. No, that's not, that's USB-C to micro, USB-C to USB-C, USB-C to USB-C, USB-C to USB-C, USB-C to A, that's one of them. Here we have another one. I didn't mark this one. I don't know why. Normally I mark them. Here we have another one. Here we have another one. And here we have another one. And here we have a last one. This one. This one is... No, it's not this one. Where is it? There's one where it wasn't on both sides. This one looks okay. So let's test the cables. One after the other. Where's the tester? Here. I don't remember which one. This is only USB 2, that's for sure. I don't think, looking at how flimsy it is, I don't think it is shielded. No, it doesn't. It's not detected as shielded, and I don't think it is shielded. Let's switch off the soldering iron. It seems to work for now. No, this is not shielded. So we don't need this one because we already have an unshielded USB 2. It's this one. Although, let me mark it. USB 2 and but it has RP. So RP, what is RP? Let me show you again. RP, it's resistance pull up, and there is in the USB-C, it actually tells that this is connected to a USB, so it indicates that this is a USB-A on the other side, the RP, or actually that this is that the other side is a host. This is what the RP is for. If it's not there, sometimes the USB-C which you connect to will not provide power. And if you don't have power, or the other way around, and if you don't have, so this is for, why is it? Why is it? The RP is just to indicate when you plug to the USB-C that the other side is a host, because USB-C is generally a host. Although in USB on the go it can switch, it is generally a host. And the RP inside is 56K. Yeah, and I need one transistor for that. Let me mark the cable. If you don't have that, some devices might not start. I think they can still, they could completely ignore and just use the power coming in. I think they want to do some cable detection. It also allows to determine which, although it's on both sides normally. Do I test on one side or on both sides? RP, I test on both sides at once. I think it is on both sides. No, it's not on both sides, because in here you should only have the USB connected. Yeah, okay, now I remember what it is for. In this USB-C connector, you only have one side where the USB data plus and data minus line are. And for the device to figure out where you plug it in, which side it is using the CC wire, and on the CC wire there's RP. And this is how it identifies the orientation of the plug. Now, on some devices, it's completely, you don't test which side it is plugged in, not which side, but if it's flipped or if it's unflipped, because you will use just all 4 data pins and you will bridge them together. On USB 3, although this is a bit different, because you need to, you need to figure out which are the TX and RX lines. So it's more important for USB 3. For USB 2, I don't really care about RP. But let's mark the cable, because I love marking my cables. This is a USB 2 no shield. USB 2.0 RP and shield is crossed. No shield. Up. Okay, this cable is now. You don't see the details now. This cable is now marked. up. I need something to clip it. Yeah. That's clipped. Okay. I don't need this cable anymore. This is also probably USB 2 on shield. Although it might be shielded, it feels nice. Let's test it. Let's just immediately test if it's shielded this way. No, it's not shielded. It's 200K. It should be 0K. Then the 200K are because I'm touching it. Yeah, this is not shielded. And it is probably also USB 2. I don't know why it just, yeah, they skimped on the shielding. Maybe it could be shielded, but only on one end and not the other, and that's still possible. So see, no shield. And if I touch here, no, it's not shielded. And yeah, so it's not going through. So it might be that there's still some shield going to the cable and only attached to one ground on one side, but it's not going through. But then it's bad shield, and I don't think that they would do bad shielding if they would do shielding. The only way to figure out is cut it. I don't want to cut this cable. And I don't think that you would do shielding, but not going to both sides. What we can test, yeah, actually what we can test if the ground is shielded. This is completely possible to test. Let's get. So it's only one of the things. Let's get. Where is here a plug? And I'll show you what I mean. And there could be some good things. Let's go to beep mode. I don't want to measure the continuity. I don't want to measure the voltage. So, can I use this? No, I can't. Because this is. Yeah, the shield is already connected to ground. I can't use it. Yep. I have to test another USB plug here. This one. Now we can test if the shield is grounded. No, it's not. Here we're connected to a shield, to the ground, not even that. So this is not really a USB compliant cable. I'll mark it also. I'll mark everything. I just need a tag. So it's USB 2 RP, but no shield. It's like most cables, most cheap cables. I have a good cable, so I can test them. Maybe we'll test also. I'll show you that sometimes on USB-C the shield is grounded, but here we have USB 2 RP and shield, no shield. I could have a number scheme so I can actually write it on the cable instead of writing it on tags. That might be a possibility. We'll test if the USB-C shield is grounded. Just finish this. Just so I can show you that sometimes they still do it. I need my USB-C breakout boards. And this one, yep. So using my breakout boards, we can test if the shield is grounded on this side. I've seen everything. I've seen the shield grounded on one side, on the other side, on both sides. I've seen all the configurations. So here we have shield, here we have ground. See? This time the shield is grounded. It makes beep, but only on one side. It is not grounded on the other side, and there is no connection between both of them. And yeah, it's maybe there is a shield going from here through the cable. I really doubt it. Without opening, we can't figure it out. Let's test the other one to see if they did it on one side or the other, so I can really show you that there's everything in cables. You can find all qualities, and this is why I have a tester. Nope, here it is not grounded on either side. Is it grounded here? I think it's not, but we'll see. No, and here, yeah, on this one, it is not grounded on either side. The tester didn't make any false positive currently. This is good. Let's test this. Is it a good cable? Why didn't I mark it? Well, let's test it. I don't have a good cable. And I have also magnet cables. So, what does this one say? This is again USB 2. Yeah, this is USB 2 only. Does this have shield? Oh, it has shield. See? When I connect the two shields, it has shields. And this means that normally it is also grounded. Then both sides are grounded. There's shield from beginning to end. Let's test it. They can still cheat. Yeah, it is shielded. So that they could cheat. They could connect the ground directly on shield on both sides and have no shield in the cable. Completely possible. Again, I cannot without cutting. But generally, if they they ground both sides already on the shield, it's probably a good cable. So we can test it if they. So yeah, but the tester can't test if it's really passing through shield. You have to cut the cables for that, or use some other trick, analog trick. But I don't have it. Yeah, so it is grounded on this side. It's passing through on both sides, so there's no point in testing here because the shield, the ground is already there, and we know that it is connected on both sides. So the tester works for that. This is already quite good. It is almost production ready, this tester. So this is a good cable. This is a good USB 2 cable. I will keep this one, and I will not keep this one, because this one, although it seems nice, it is not grounded. It feels nice. I like this nylon fabric, but it's not a good cable. Yep, not a good cable. We'll verify. Here we will verify if it's grounded on one side, but I'll mark it. Here, I'll mark on the back. This is where it's no ground on both sides. Zero G. Let's mark it 0G. Zero G means there is no ground. On this cable, we have AG. No, CG, because it is grounded on the C side. CG, and not on the A side. On this one, it might be grounded on the A side and not on the C side. Let's measure it. I remember I've seen all combinations. It is grounded on the A side. See? On this one, it's grounded on the A side, and it's probably not grounded on the C side. Let's USB breakout board, USB-C. Yeah, and it's not grounded on the C side. You see all kind of cables. I'll mark this one. Put a hook and loop on it. Let's get a tag. So we've seen 3 combinations already. No shield at all. Grounded on one side, grounded on the other side. I don't think there is one where there's shield and it's not grounded. I think I haven't seen this configuration. We'll check it out, but I think I haven't seen it. It's for the blue one. And for the blue, we will mark that it is USB 2. RP was in there. There is no shield. And it's AG. So the A side is grounded, but not the C side. Next time I know it. When I say shield, I mean the shell, but then there's a shield cable. We need one for this. Let's get another marker. And this one I've tested, yeah, no shield. This is weird. We'll see this one afterward. So this is USB 2. It has RP and it has shield. And with shield, I mean shield plus ground. I'll make it also ground. I haven't seen any only shield yet, but I'll still mark it because in the future I might find a cable which has shield but which is not grounded on any side. For now, I'm happy with my USB-C tester, with my USB-AC tester. It's this one, and I will keep this cable because it's a good one. I don't know where I got it. Oh, it has even a CE marking molded in. I don't trust the CE markings because there's no, it's a self-certification. And is it CE? Yeah, it seems CE and not China export. Okay, I'll keep this cable. Next one. Oh, this cable. These are fun to test because these are magnet cables. See, you leave this one in the phone generally, so there's no dust coming in, and it's easier to just then connect the cable to the magnet cable. But on this ones, it's very rare that they have the correctly the shield and so on. You see, I've tested it. It has magnet, it has charging, power delivery, charging, yep. It has data, it uses 11 pins. You see here 11 pins, but it's because it's flippable. But it has power delivery. So if we test this cable, it doesn't have shield though. And I've seen one where where this metal here is used to get the power delivery, or the CC wire actually. The correct name is the CC wire. The LED goes on in here, but no LED goes on here. That's perfect. Yeah, you see RP. Power. Yeah, power is there. Maybe it was misconnect. The connection is not super good, but it's good enough. And it doesn't have shield on any side. Let's test it. So it's not going through, that's for sure. Let's test if it's grounded on one of the sides. No ground. No, it's not grounded on A, and I don't think it is grounded on the C side. No, it's not grounded on the C side. Up. But it's and you see different magnet wires. This is just also this one. Ta-da! It has a USB-C inside, so you can either use USB-A or USB-C. And this one has only 11 pins. Sometimes you only find 5 pins. Sometimes you'll get all 24 pins. I have all kind of cables, and so it's not. I will write that it's not shielded and it's not grounded. 0G and shield is crossed up. Okay. It still works for charging. It works plenty. It works fine for charging. And it works fine for USB 2 data transfer. So it's not ideal. Now I have 2 good USB cables. These are, well, 2 good, not completely good. This is a USB 3 cable. You see, because it's blue, generally blue indicates it's USB 3. And you see these tabs on the end. And if we plug it in, one side, the other side, now, yeah, USB 3, now we have, so this is soldered correctly because I verify the USB 3, the 2 USB 3 pairs. So the disconnector is soldered correctly. For the first time, it's good. And it doesn't have shield. I wonder if it's grounded on one or the other side. I would expect that it's grounded at least on one side. Because with USB and I think this cable is shielded, because USB 3 without shielding is really hard to do. But it's just not connected to both sides. So it's not grounded on this A side, that's for sure. It is not, there is no shield passing through the cable. I think it will be grounded on the C side. Yep, it's grounded on the C side. Let's mark this cable. No shield, and USB 3 no shield, and it is CG, grounded on the C side. Now my last good cable is really short and it's really thick, and generally when it's a thick cable, it means there's lots of material and lots of connectors. And I know that this one is USB 3 shielded and it's grounded, and it's grounded on both sides. We'll test it. You see already when I touch, it knows that it is shielded and grounded. And if I plug it correctly, yeah, we have RP, USB 3, shield, USB 2, and power. So actually, this works. My USB AC cable tester works and it tests shield correct. Now, yeah, I don't have any cable which is not shielded on both sides. Let's try if I can cheat. Here it's shielded on G side. Can I cheat by just making this? No, it needs to pass through for it to work. Yeah. So I have pads here, but I can't test them. These pads are when you have shield. Oh, this is USB 3 and it's not, it doesn't have, yeah. When but I don't have this cable. When there's a cable where there's a shield going from one end to the other end, but it's not grounded, then the shield will not light on. This shield means it is from one side to the other, the two shells are connected and they are grounded. In case they are not grounded, you have the pads on the back. So what you do is just plug one side, and if you touch the other side with the shield, then it will ground the shield and it will light up the shield part, the shield one. Will it? Will it actually? Let me try again. So the shield LED goes on if, so there's power coming in, if the shield A is grounded and the shield C is grounded. Yeah, it verifies that both shields are grounded. When shield A is grounded, this PMOS, it's a PMOS? Yeah, this PMOS is pulled low, so it's enabled. And if shield A is grounded, then, so that's how it tests it. Then it passes through. So if you have a cable which has shield but not grounded, if you do it this way, this is what the pads are for, then shield comes up. But yeah, as you've seen, these are all my cables, and I don't have a cable which is shielded and not grounded. But we can test if it works this way, because this is, but it doesn't work. No, it does. Huh? Didn't it? This is, oh, wait. Okay, it doesn't work. So I made maybe a mistake. It still needs that this is shielded. It still needs both sides to be grounded and verify both sides. So the pads are not useful for anything. I can remove the pads. How can I do it? Yeah, because here verify really it only goes through the shields. Yeah, and it verifies not if this is shielded, but they verify if the shell of the receptacle is shielded. So actually these two ground pads can be removed. I can remove them, they're not useful. I would like to have a cable which is actually shielded. This one, I think this one is shielded. But it needs to be on both sides. Okay, can I improve this? I wanted really to be able to to have... So I know this cable is shielded, but it's not grounded. I still want it to be detected as shielded if I do it this way. I think if it's shielded and it's not grounded, then... but it's not an issue. Yeah, I need to fix that. How can I fix it? Yeah, it verifies the pin, not the shield. Okay. What I could do is, what I could do is have the pad here in the middle, so you can touch this way. And then you shield one side. Yeah, this is what I'll do. I'll move the transistors a bit to the right, and I will have a ground pad in the middle. And then when you short the ground pad to this shell, or when you short this ground pad to this shell, then you make the connection. Okay, I'll do it this way. And I'll remove the ground pads from here. This will be version 2. But version 1, see, this is really USB. This is not USB. Okay. But else it works. And I think this last case is really rare. I don't have any cable which does it. But that's to be done. Else it works perfectly. I really liked it. And I like this small cable, this USB 3 cable. Yeah, it lights everything. And I could put it in blue. Why did I use shield in yellow and not in blue? I don't like the blue which is there, and shield, yeah, I use blue generally for data or other things. Shield is very much yellow, and also my other testers, shield is yellow. So I'll keep it yellow and I'll not make it blue. But I'll put some shield pad and some ground pad on the top and not on this one. I don't know what I thought when I did this. And it's really easy because this is just a 2-layer board. This side is VCC, this side is ground. So I just have to open the mask right here and remove it. And then I can mass produce it. So in something like 2 or 3 weeks, you might see this USB AC cable tester in my shop. Yeah, that works. So what do I want to do? I have other boards. I have several boards which were coming in. I ordered these boards, and 2 weeks afterwards I ordered another board. They came at the same time. But this works. So this USB AC cable tester works, except for one case, which I don't have any cable to test. Do we want to do the other one? Oh, still have a bit of time. So let me present the other project. And then I'll work on the last one. It's a surprise for our next stream. Let me first clean this mess. I'll write down what I need to do. Yeah. Here, these 2 ground pads, G1 and C2, these are wrong. Where is pen? Here. We have removed 1 ground and between A and C on top, on front. Else works perfectly. I like this tester. And it didn't trigger when only one side was grounded, which the other one, actually, let me show you. My old, here, this one, USB cable tester version 0. This one is okay. It doesn't have the mod, the fix. C, this one is shielded on the C side, and when I was plug it in, there's no battery, so it won't work. Let me put the battery in. No, this one won't work. Yeah? Why don't you detect the shield? Ah, no shield. No, but the C is grounded. It's another cable which triggered it wrongly. Is it this one? AG. You see, when I was plugged in this one, the shield was lighting up because I only tested if this side is shielded. So this is a false positive because it's not possible to test if the cable is shielded when you only plug one side. This is why I had to fix it in version 2. Yeah, in version 1. This is version 1, this is version 0. Up, that's done, that works. I'm happy. It's not the final one, but I won't do any production. I won't do any prototype anymore. I will put the ground here and I will order it. That's it. There's no need for me to make a prototype, and I will already order a couple of boards. Need to make panels out of it, and I will keep them in red. So the white ones are USB micro USB cable tester. Black is USB-C cable tester. I will keep red for USB AC cable tester, and I will have another cable tester, but this is currently being designed, so it still needs a bit of time before I release it and before I can talk about it. I already showed it to you actually in one of my streams. It tests a lot of cables, but I'm happy with this prototype. Prototype works. Let's keep it with my AC cable tester on top. I don't need to make another one. That's version 0, 2, 1. Let's clean the task a tiny bit before we move to the next project, because we have a bit of time and this one really fast. So pen goes here, this goes here, tweezers go here. I need to clean them. Up. Let's get some alcohol. Up. Tweezers are clean. Tweezer 2. Clean. USB-C cable goes USB 3. The cable I like, it remains with me here. All the USB-C cables go in here. This comes plugged. Tack, and I can present the next project. Coin cell holder, I don't need anymore. Let's put it back on the shelf. Up. Side cutter. Flux. That's the USB-C tester. This goes to my prototype stack. USB goes here. Transistor SMD book go here. Oh, I still have this one. This goes here. My USB-C breakout board goes back on the shelf. Put back this USB. And I'm happy with the footprints. I've tested the footprint for the A and the C connector, and they work. Hup. This is the next project. Scissors. That's trash, that's trash. That's the alcohol. These are the tags. Up. This is USB-C tester. This is cool. That's good. Up. So this heating plate is completely not temperature controlled, and it goes, I think it goes up to 220. So for some plastic it's not good, but if you are quick enough, it works okay. Maybe if I have time, I will build temperature controller. It's not hard, it's just, it doesn't use a lot, it's just 400 watts, so I can use a 2 amp triac. And then a K-type probe, which I fit free. Well, we use 2 K-type probes. One which I can place on the board, on the target where I want the temperature, and the other one just as safety, which I can put on the heating plate itself. Okay, so let's move the pizza here from the SMD part. We have the USB-C cables. They go back to my USB cable collection. Now, let's do the other project. This is this project, and to illustrate it, I need my box with, where is it? Oh, did I? No, did I? Display connector. Did I clean it already? USB-C, radio lights, and blood pressure. Yeah, I think I did, but I can still show it to you. Has to do something with LCDs. So you might know these LCDs or these one. These are 16 characters, 2 lines LCD displays, and they are driven using this HD44780 I don't remember exactly, but it's a chip which is used a bit everywhere. So you find them as LCM or LCD 1602 because 16 characters, 2 lines. Sometimes they are with anode and cathode. So this one doesn't have anode and cathode to have some light. Does it? No, it doesn't. This one does. There are 16 pins, anode and cathode additionally, and this is the LED light. Some come in green, some come in blue. You find them in lots of different ways. You even find with four rows and more than characters, but most of the time it's really the 1602. No matter what, even if you have only 1 line, if you have 4 lines and so on, they all use the same chip inside, or at least the same protocol, which I did right here. Yeah, HD44780. This is the protocol which is spoken here. So you have, I think the lines are shown here. Yeah, you have all these pins which are used to drive it, And the problem is that these are plenty of lines. So you have 8 data pins and then 3 control pins. 1, 2, 3. Yeah, exactly. You don't have to use all the 8 data pins. You can use only, there's an 8-bit mode and there's a 4-bit mode. In the 4-bit mode, you just use 4 of the pins. You still need the 2 additional ones. You can ground one if you don't want to read the answer, but if you just play with timing. So you need at least, that's the minimum. You need 6 lines, which is quite a lot just to drive an LCD. So what people came with is these modules, which are called I²C backpacks, I think, LCD I²C backpacks. And the idea is that you put them on the back, like so. And then instead of having the 6 lines or more, you actually only use I²C. You have VCC and so on. You only use I²C. And actually, how it's done is this is just a GPIO expander, an I²C GPIO expander. The problem which I didn't like is you need to know the protocol of these chips correctly. You need to know the timings, you need to know the commands, and it's really, really a pain to start it correctly. The initialization sequence is a pain. You need to go tell, okay, now I'm in 4-bit mode, then you need to send clear address and so on. And it took me a lot of time. And also, because it's over I²C and sometimes you just wiggle one GPIO, it's super slow. So this goes up to megahertz, this chip, at least 1 megahertz. This is 100 kilohertz to 400 kilohertz. And sometimes, depending on the code, it's only twiggling 1 bit. And you have to write all the time 2 bytes. So the address plus 2 bytes to just write 1 bit over I²C. So it's super wasteful. What I decided to do, and because you still need to know the timing, this is just a GPIO, I²C GPIO expander. I made this board, and this board is actually not a GPIO expander. Well, it could be used as, but it has a chip inside which takes care of all the initialization and so on. And afterwards, you don't need to wiggle the pins. You just say, I want to write on line 1, here are the characters, and you just send the ASCII characters. You don't need to know the table. And the chip on here will just take care of sending the data on the chip. So that's the board. This is this board, and we will test it. And see, normally, so when you have the display, you need also 2 things. You need to pull up the E line. Was it E? Yeah. You need to pull up the E line, and you need how is it called? A potentiometer. The potentiometer on the LCD just has to do with the temperature, the height, the pressure, and so on. And sometimes you don't need very often. You just put it to VCC and it is bright. But sometimes you just need to trim to adjust the bias. Oh, I don't know exactly what it is, but you need to adjust the V0 value. This value V0, so the contrast is correct. This is why on the Game Boy, for example, on the right side, you had a scroll to adjust the contrast of the LCD. It just depends on the temperature and the altitude. Maybe some other parameters, but these are the 2 important ones. And yeah, so you needed that on the board. This is included on this board. It is also a bit smaller than this one. I think it's 1 line smaller. Yeah, it's 1 line smaller. So it is I²C still, which is good. And yeah, it takes care of the whole initialization. You just then tell it on 1 line, write these characters. And because it's directly connected on the pins, it is super fast. You cannot speak as fast even with the 400 kilohertz I²C. The writing on the chips is done faster, and it also can do it correctly because it will read the E line or the D7. I think it's D7 to know if it's busy or not. And that's the board. That's the board I meant. So I call it the QR code is really small. Can I scan it? This is really small. Yeah, the QVoodoo I²C to HD44780 adapter. Yeah, adapter, and it's for LCM 16. Let me check this. Scan. Up. Will it focus and will it be able to decode this QR code? I don't have it the right way around. Yeah, too small. Okay, can't make it. Also can't focus on it so near. Okay, it's too small. Let's try another barcode scanner. Maybe this one will be able to do it. It won't because this is the wrong way around. It's too small. Maybe it's just my phone which can't read it, but I can't make it bigger because I need to write it. I can make it a tiny bit bigger. Instead of calling it DB, I will just call it D0 and so on. And this allows me to whip. Where did you find barcode? I don't know where it found a barcode. Let me tell it that this is settings. This is the other way around. QR code, where is it inverted? Invert scan, here. Let's see if now it can find it. Yeah, okay, it works. It didn't work with the other one, but it works. I think this link doesn't work correctly currently because this is not a release product. I don't know if maybe I will make a product of it. I don't know. Depends on the demand. Okay. So let's solder it and let's test it. If it works. That's the task. Do I want to solder it directly on this one? Probably yes. Maybe I will solder it on the board. Let's solder it on another one where we have the LEDs, because I also want to test. What I also created is that you can control the brightness of the LED. So I'll just use a module which has LED. And the other advantage. Yeah, most of these modules are 5 volts powered, and now it's really rare to find. Well, it's rare. It's hard to find microcontrollers which block 5 volts, and also even which have 5 volt compatible, which support 5 volts, so tolerant to 5 volts. The advantage of this one here, you can provide 5 volts, but you provide the pull-up for the I²C. You can set the I²C to 3 volt, and still provide the complete power for 5 volts, and it will work. This is something which is really good. So yeah. Now you don't have to. Here you see this is 5 volt, and most of them are 5 volt. Sometimes you can find them for 3 volt, and they have a small booster here. Oh, small. Yeah, it is a booster. Yeah, I think it's an integrated booster. This one doesn't have it, but I have some of them which have the booster included. This one don't have it. I know I have some of the LCDs with booster included, which can talk to 3 volts. Here, this one, see? This booster is included, and this one is capable of being driven by 3.3 volt. Using this module, you don't care anymore. You will provide VCC, whatever you need, and then you pull it up. There is also the 2 I²C pull-up resistors if you want to add them on the board, but normally you want them to add them externally, because this is the device and you want them to add them in the host. And this replaces completely these things, so I will not use these anymore. But we can still use it as GPIO expanders. They're expensive. GPIO expanders are quite expensive, and I'll probably just keep them for the GPIO expander as GPIO expander. And this is, I think the GPIO expanders are more expensive than this microcontroller. Weird, but that's the way. Yeah, let's solder it. And there are not a lot of parts. This is done really fast. Up. So I need these microcontrollers. I need some trim pots. I think these are the ones. Yeah, it's between 10 and 15K trim, which you need. So I used 15K. Yep, this is trash. I will solder it directly on this one so I can test it. So yeah, this is perfect because here we have the LED. This is not a 5 volt one. This is a 3.3 volt, and I will use a 5 volt microcontroller to drive it. So we will test it this way. And there are a couple of things which I need to solder. These are 2 capacitors. I don't remember what is this. This is an N-channel MOSFET. Yeah, let me just get the schematic. Backlight. Yeah. Backlights. Yeah, you can change the resistance. If you think that the resistance is too high, you can just change the resistance here. Let me get this one up. So in my projects, up here I²C boards projects, and I will have the schematic. I will show you the schematic. I don't need to print it, there are not enough parts for that. It's done in a quickie. 100. Ah, we have 3 capacitors, that's why. See, 1, 2, 3. And then, oh, I do it correctly. I have 2 resistors for, what is this? This is 100 kilo. Okay, so let's solder everything. Yes, okay, this is the inline, and the tracks are good enough. You can also set the address, like in these modules, this one, you can somehow set the address A0 to A2, same here, you can set the address. It's just solder jumpers. Let's switch on the soldering iron. And let's start. The code is almost ready. I think the code, I need to change some of the pins, I think. And I need to change the default address, but this is just something in the firmware. We will check it afterwards. Up. Ah, is this footprint correct? This is the first time I use this all the way around. These trim pots. And yeah, these are very, so these trim pots are a lot more robust. You can change it very often. This one, I think you can change it on, you can turn them only 100 times, but at least they're small. And I don't think you need to change very often the contrast. Once it's set, it's probably good enough. This is why I didn't put the large expensive wire. I wanted my board to be really flat. But the footprint seems to be correct. Solders well on one side, and yeah, the footprint is correct. I'm not sure if anyone is interested in this project, but it's for me, so I don't waste time anymore. I love these modules. They are very easy to drive. They're cheap, they're easy to drive, and I mean, most of the time you don't need a lot of text. It's completely readable. So I'm a fan of them. I know these are capacitors. This is also a capacitor. What is this? I would say this is for the E line, the 100K. We'll check it. Yeah, the 10K. Oh. Well, yeah, it's for the E line. It's the 10K. $10K, 5% is good enough. And also it will be the opportunity, because what I did is currently microcontrollers are super expensive because they are not available anymore. So, well, not available because of the IC shortage. You can find a lot of microcontrollers. The ones you find are more expensive. This microcontroller is an STM8S. They were only 30 cents before. Now they are $1.70, something like that. And still, it's the least expensive part, because there is, was it here, this one. This is the part I'm using, the STM8003. And actually, the difference between the S003 and S103 is the EEPROM. The quantity of the EEPROM is theoretically not the same, but in practice, it actually is the same. This is why I bought again some of, well, on the one I found, this is why I bought again these ones. the 003, and I will check again if there is 128 or 256 bytes instead of just less for the 003 version. So here we have 3 capacitors. This is probably 101. Is it that? Let me check the schematic. This is 1, this is 100, and this is 1. Exactly. Capacitors. Tweezers. I need to put some solder on the pads first. Backlight, I need to. This is. What is this? I don't remember. Oh no, this is 1K, this is 100K, this is for the inline protection resistor to not drive the gate too hard. This is 100. The 100 goes here. I think for this microcontroller it's not too important to have so many decoupling capacitors. I could probably skimp one, but I just don't want. I don't want to spend time debugging why something doesn't work just for a 1 microfarad capacitor. It's not worth the time. Sometimes you just need to remove capacitors because of the size. But here we have plenty of space. Okay. Then we have the 220. This is for the backlights. Because we want really bright backlight. This is the backlight LED BL. Next is 1K. Do I add the pull-up? No, I don't, because this will be 5-volt powered, and my test board will probably not be 5-volt tolerant. Oh, it will be tolerant though. Do I add the pull-ups? I don't know. 100K. 100K. This one. And then this is an NMOS. Which one did I use? Probably I used one which is far too powerful. Probably I used this 2002. And a BSS should be plenty enough, because I'm not sure you're driving more than 200 milliamps. So let's test transistor. Oh no, okay. I didn't use the one which is too big. I used the smaller one, which is plenty enough. I mean, more than 200 milliamps for backlight is quite a lot. It's an NMOS, and it's this one. Let's get this NMOS out. Too many out. I just want one. You go back in the package. Damn it. Sorry, I'm sorting my... probably don't see it. I'm sorting the mess I made with the MOSFETs. I peeled too much of the tape off. in, and I want this MOSFET. Up. Let's test up. That's it. Do I want to add the pull-up resistors? I will have 5-volt tolerance microcontroller. Yeah, I'll probably use again. Yeah, I'll try. Yep, I'll use a 5-volt tolerant microcontroller. So let's just put the resistors on there. Oh, I can use the embedded resistors. Ah, okay, I don't have to. Yeah, I can use my bus voodoo with the embedded resistors. Yep, so I don't need to. And now I just need the microcontroller. And then I can solder the remaining headers for programming. And in programming, I need to verify if the pinout is correct. I think I've changed it. These are just GPIOs, so you can make what you want with them. It's just the I²C, which is important. This is pin 1. Let's tag the other pins. Okay. Now I can drag solder. But I need some flux. Up. I can solder the headers. Drag soldering again with some flux. Looks a lot better. Solder aside, I didn't add flux. Let's add it immediately. Okay, that's done. Let's clean the flux. Oh, do I have? I don't have any more. I need to get back some of the sponges, but let's use some wipes. Good enough. We still need to solder some parts, but these are through-hole parts. Looks nice. I like it. I like how it is. I still need some header. Yeah, I can't directly put it. Could I? What's important? No, it's not too important. I can still read it. I thought about putting the programming information on the top, but it's only for me, so on the back it's plenty fine. I need some headers, some 90-degree headers and some non-90-degree headers. Here and here. Here are my boxes. So, I need some long headers with 16 pins. I can use plenty of smaller ones. I still have some long ones. To have some metal not golded. Yeah. 16. Tuck. This is 16. And then I need 90-degree headers. Here's already 4, and I need second times 4 to program it. And we'll check the code afterwards. The code is not, it's not, it is an I²C slave, so it's not, and normally it should work pretty fine. I wanted to solder directly, so let's solder these things first. These headers, fronts and fronts. And yeah, this is important. I will use this same my I²C slave code, this microcontroller for another project. This will be yet another stream. If it works correctly. One side, let's have the other side. That's correct. Flow, flow, flow. Okay. This is higher, so I can have this headers this way. Even they stick out, it's not too much of. Oh, although I wanted to have it flat, so I will cut them. So because I need to cut them either way, I will solder. Maybe I will solder it this way. I'll solder it this way. I don't need to cut them. Here they're sticking out, but everything here is already sticking out a bit. And if they're sticking out, it's quite useful because I can put them on the debugger. That's one side, and normally, if I did it correctly, it should fit this way. Yeah, this is ground, and here we have VSS, so it fits perfectly. Let's check if everything works right. VSS, VDD, what should I call VCC? And then V0, RS, RV, E, B, and here they call it D also. I'll call them D, so I have a bit more space and I can increase the logo for the next version. I don't know if I will make a large number of boards or if it's just for me. At the beginning it was just for me. If there is demand, but I don't know if there is any demand. If you see the video and you want also to buy this board, just let me know. Write me an email and say, hey, please, I wanted to have it in the store. And if enough people do it, I might have a production run. Else, I will just publish it. And you can make it yourself. It's not hard, there's not a lot of components. Just the hardest part is probably programming the microcontroller, which you don't need to do if you buy it. That seems to sit fine. That makes it a bit larger, but we're fine with it. Let's clean our hands to remove the lead, because yes, I use lead solder. Leaded solder. And then we can start with the code. Here is this part. I need a programmer. ST-Link. Yes, I don't care. It does ST. 4 pins. Female to female. Always the box below. I need to plug the other camera in so you can see things. For charge the battery, up to plug the HDMI cable, up, switch on, that works. Here in camera mode, do I have to go in camera mode? I think it's faster. Let's go to camera mode, and okay, it's not this way. I zoom, level, need to put it in full HD. Okay, now I should have HDMI, HD output. This is something else. Next project, this goes here, and it works. Up. And why did it switch automatically? Okay, maybe when something goes on, it switches automatically. This is weird. Up. Up. This and this. And you zoom out. Oh, it's already zoomed out maximum. Up. Up. It's getting a bit heavy for the arm. But it's holding. Is it holding? It's holding good enough. Okay. But the cable is not long enough. We'll do it afterwards. So we need 5 volt or 3 volt. It's not a problem. This microcontroller, the advantage of this microcontroller is that it can do both 5 volt and 3 volts. Then we have reset and swim. Reset is gray, swim is this. And I don't remember which is what, but I have a board. I know that this is ground. Then we have white, which is, I think, 5 volts. Then we have swim and then reset. Swim is... Actually, I did plug it wrong. Swim should be here. Swim is pink. Swim and reset. Now I should be able to program it. I think the code I have is probably not the right one. Let's check. Switch to full screen. Data, project, I²C, firmware. I just want to test if it flashes. Oh, STM, I think, yes. Let's put it in another screen because I need 2 of them. Although I don't need 2 of them. Yeah, I need 2 of them. Okay, let's plug it in. Up. It already did make a short. This is good. Make flash. Okay, it cannot flash. That's already not a good start. Pin 1 is okay. Wow, the other ones are not really well soldered. Yeah, don't consider this as soldered. Nah, I need to solder again. But do I have it correctly? VCC, ground, swim, and reset. Swim. Yep, I did mix the stream and reset lines. This is why it won't be able to flash. But I still need to solder it. Because this soldering on this side is not very good. flux. Because I created bridges again. Okay. Okay, now it looks better. Alcohol wipes, you don't see anything. That's not important for now. Okay, that looks a bit better. Yes, it worked. That's the start. You can zoom. Not too much. So we did flash it, but I think the code is not correct. Vim main, I think. Main.c. Yeah. Did I make some changes already? No, I'm already on the full commit. So you go somewhere where you're not in my way while I program. Let's put this on. Let's check if everything is okay. Yeah, see, the slave address is not correct. I also don't read the bits currently, but that's for later. Let's use 47 for now. The backlight LED is PA3. Backlights. What do I use? PA3, that's correct. Then we have RS PD3. RS, no, it's PC3. So this was for my breadboard prototype. Then we have RV read write. This is PC4. PC4. Then we have the E pin PC5, PC5. D4. It's PC6. That's okay. D5, PC7. D6. It's PD2, and D7 is PD3. D3, that's the address, these are the commands. Do I need something important? I don't remember why I have the lookup table for. Nah. Might be some reason. And the rest should be fine. I mean, I still need to program that it reads the 3 bits, the last bits, for setting the address correctly. But for now, for just testing, it should be fine. Like flash. I know it bugs. It doesn't flash the first time. I don't know why. So I already make. Okay. Overflow implicit. Why is an overflow? I²C address 1. There is no overflow. The address, did I read? No, 47. There's no overflow if I just switch by 1. Overflow in it thinks it's an. Oh, sorry. And it thinks it's a signed int. Oops, sorry, that's not what I want. 280. This is not a signed integer, it's an unsigned u, and we will, I think this is all I need. No, implicit conversion. Do I need to make this one unsigned? Yeah, that's it. Okay, it was able to flash, and now I can test with my bus voodoo if I can talk to it. Up. The cable is also not long enough, so you won't be able to see anything. I need to bring a longer cable just for the stream. Long cable, this one. side. Let's plug in the other side. Tuck. I can actually write some test code already in the beginning, so it does something, so we can test it directly. We'll do it two things at once. Let me get some extension. This is maybe long enough. Extension here, extension here. Just by changing the code, I can make it display something already. Do I have still test code here? No, I don't. I just have the init and that's it. And I think it is not switched on. Clear display, mode line 1, set line 1 address. Okay, this is to set line 1. We need this. We need to turn the display on. I think it is on per default. Isn't it? Is it? I don't remember. No, init probably doesn't display it on. This is display on. This is set line, and then we just need to write data, I think. Mode display. Here we have entry set function, CRAM address. Yeah, we just need to write data. Why do I do that? I don't remember. Yeah, it's probably the way it is. DRAM, that's the address. Oh, that's to write on the RAM. But we will write on the DRAM. I think it's this way, but we need. Do we write in the DRAM or in the CRAM? I think it's DRAM. Yeah, I think it's this one. So let's just write h hello input data is equal to h. Let's try it out. Plus that, yeah. Input data is already declared here. Up. H. Let's flash it. Now it flashes every time. And if I did it correctly, it should display something here, but I didn't do it correctly apparently. Or is it still in reset mode? I don't think it is. Maybe I have to set the contrast because I didn't set it. I will try to switch on the backlight to indicate that everything is fine. Let's switch on the backlight. I have the brightness. This is here. I will set the bright. Oh, something happened here. I'll set the brightness to maximum. This is just to test if the code works. And if the LED works. Okay, it manages to flash every time, so on the breakout board it didn't. The LED doesn't go on. Why don't you? PA3. Backlight, PA3. That's not the only problem. Well, this is a problem, that's for sure. But this are problems too. PD. But it still doesn't display anything, and the LED is not on. Not good. Why isn't the LED on? This is something. Did I use 3.3 volt or 5 volts? 5 volts. That should be fine. Let's measure. So we have ground here. VCC, is it 5 volts? Yes, it's 5 volts. Now the 5 volts should go here. So here we should have 5 volts. Here we should have 0 volts. We don't. Ah, no, it's not 0 volts. Ah, so it seems that the LED is on. This is the voltage drop. This is the, so here it should be, this should be 3 volts. This should be high. Well, it's not. This PA3 should be high. This is low. Okay, so it's not sending. This is already a pain. Backlight. Why is the backlight not on? I think I've tested this. Soldering looks correct. Ground, and here we should have 3.3 volts. We don't. We simply don't. And we also, this one also doesn't work. Data direction. Did I hard code anything? No. Let's see on the lights. These are the pins. This is I²C, the wake up, PVM. Oh, so the channel is hard coded. This is push pull. Oh, these are the fields. Configure channel outputs. This is third channel. PA3, let's have a look at the data sheets. Hub data sheets. The reference manual. Hub pinouts. PA3. Let's have a look at here. PA2, PA3. This is timer 2 channel 3. Is it the one we're using? We are using timer 2 channel 3. So this should be fine. And what if I just make it the middle? The LED still doesn't go on. We know it's power is coming here. We have 5 volts inputs, and we don't draw any current because else we should drop something. So the MOSFET is not switching on. But we also don't have the PWM signal coming here. It doesn't look like any PWM signal. It's just too low. It's at 0 volts. No, something is not working. Damn it, my code was working on the breadboard. Is it the other way around? PWM off. This is high, this is low. We only use 8 bits, I think. Yeah, we only use 8 bits. It goes only up to FE. So if I make FC. No, LED is not on, and we have something. Is it a PWM signal? I don't know. I need the oscilloscope for that. Let's get the oscilloscope. Oh, I think the oscilloscope is in a complete wrong there. Configuration in rolling mode and so on. acquire acquisition, that's okay. Measure, no. Cursor, display, no. Utility, no. Storage. Where is the I/O? Where is the mode menu? Here. Roll. We don't want roll, we want time. Okay. And 2 seconds is far too long. We want 10 milliseconds. We won't see anything, but it's not too important. Let me check if I have some PWM signal. No. There's no PWM signal on there. Is it held in reset? Because of the programming, that's why it doesn't do anything. What if I just provide... no, if I just connect, it shouldn't be under reset because I had the board all the time this way. But it doesn't do any PWM. Let's switch it on. Simply programming as not PWM, but a switch. Output enable. We will just not enable this output. And we will set the pin. It's not TDR. How do we set pins again? I think it's this way. Set high. We want to set high because this is an NMOS. Yeah. BL pin, BL ports. Okay, it's BL ports. Output data register, I think. That's okay, and then BL pin. And this sets it high. So this. Okay. If I measure it, it is not high. So either the pin is not soldered. Everything looks soldered. Which one is PA3? That's not the right form factor. We are on the T-sub. T-sub. PA3 is this one. SPINSS. This one. No, this one is not high. Let's completely disable the timer, because here we have a huge pepcake. The board is not starting. It is still not high. So the microcontroller is not starting. Nope, the microcontroller is not starting. It doesn't, I don't have a pull-up on the reset pin, but I don't think it needs one. I verified that it has an internal pull-up, right? Pinouts. I think the reset pin has an internal pull-up. I verified it. RST pin characteristics. Yeah, pull-up resistor. It has a pull-up resistor, so I don't need to put one. Let's figure out if reset is high. Reset is on which pin? Pin 4. It is high. Reset is high. It means that it should start the code. 1, 2, 3, 3.5 volts? What? Why only 3.5 volts? This is 5 volts? This is 3.5 volts. Okay. Now we are at 5 volts. Still no. So okay. So because the microcontroller limits it to 3.5 volts. This one, yeah, 3.5 volts. Maybe we just need to switch from 5 volt to 3.5 volts. Might be possible. Did I switch anode and cathode? Let's test. No, anode. This is the anode. This is where it comes in, and then through the thing. No. Yeah, but the problem was not that. We also had no high written. That's still not high. Are you programming the right thing? Okay, no, it's programming the right thing. Why? I don't know why it doesn't work. This is 3.5 volts. Ah, yeah, now we had 3.5 volts. That's okay. This should be reset. Let's check on this. Reset. This should be backlight. Yeah, backlight. This is backlight. This should be high, but it's not. This should set it high. Ah, maybe there's something wrong with the initialization code. Let's do it this way. And it's stuck in the initialization code. No, it's not. Come on. No, it's still not high. So it's not because of that. Is it stuck somewhere? Can I debug with swim? I don't think so. And I'm using all the debug pins, so I don't have any debug output. I also never needed one. It worked pretty well. Backlight is P3. Did I miss a configuration or something like that? Yeah, this is not high. Let's do it very early on to see if it changes something. Let's copy the code and let's do it right here. After we refresh the watchdog. Oh, I have a watchdog. So I do some good coding. Now it's on. Now it's off. I made a short. Now it's on. It's stuck somewhere. And to test it, we will make an LED debug. Is it after the I²C? Okay. It's still on when it's here. And I will expect the I²C to fail. Let's try it. Yeah, peep, 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 peep. Do peep if you want. Yep. Yep, I²C fails. And I think it's because they are not high. They are not pulled up. And do I want some pull-ups? Yeah, I will use a 5 volt tolerant one. So let's up some pull-ups. So without pull-ups, this is weird. Without pull-up, it will not start. Yes, this is where I have the code here. Wait for the SCL line to be released. It's right there. I'm waiting for the things to be pulled up. It's normal that it won't work. Let's put the pins. Let's put some pull-up resistors. So my code wasn't wrong, it was just my assumptions. Does this work? Yeah, this works. And I've actually, the watchdog should be on, so it should restart periodically, but still get stuck here. Why isn't it soldering like on this pad? Okay, now it is. Up. Why did I use 47? I don't remember. Ah, yes, because now I remember. Because this is because of the name. It's an I²C to HD44780. I had a 47 here. And you can make it a 44 if you pull 0 and 1 down. This is the small in joke I made. This is why 47, but again, it's programmed in the firmware. You can change the slave address. Okay. Up. This is pulls. And now if I plug it, it should, yeah, it switches on. So let's test again if the PVM works. Up. But it still didn't display H. That's not good. So let's try this. Okay. This works. Let's try the PVM. We don't need this. Whoop. This is PVM, and I did set it to FC. This is here. The brightness should. It doesn't. Let's put it here. Yeah, now it does. And now there should be some PVM signal. It's just the writing to the LCD, which doesn't work. You will not see it. It's on the oscilloscope. Yeah, I see a PVM signal. Okay, backlight works with the PVM signal. Now it's just the initialization which doesn't work. Is it the initialization or something else? Let's test it. Yep, the initialization doesn't work. So the initialization doesn't work if it can't read the E line. See? I hate this thing. So this should be the 10 kilo ohm for the pull-up for the K. For the E line. That's right. Is it E that should be pulled up? Or did I make a mistake again? And this is not 10K, but something more. I did write it somewhere. Here, open drain. RV. RV. So it's the wrong pin? Here. Here. Since all pins are pulled up by this, except E, which requires... but we need to switch back to 5 volts. This is a 5 volt display. Okay, still with 5 volt it doesn't work. Let's flash it again. Okay, it still doesn't work. And this is why it's useful to have these pins, so I can see what it is trying to do here. But since all pins are pulled up by GADHD except E, which requires a 10A, it's 1 kilo ohm, not 10. I think I've added a 10 kilo ohm. This is 10 kilo ohm, and this is the E, which is okay. Okay, the schematic is wrong. Well, the schematic. I'll probably just make a copy-paste mistake, so let's put a 1 kilo ohm right there and not 10. Although 1 kilo ohm? Seriously? 1 kilo ohm. It's just a pull up. 10 kilo ohm should be plentify to pull up with something else. But I wrote it in the code. There might be a good reason. So let's use a 1 kilo ohm resistor. Which camera are you seeing? The wrong one. This one. I'm 90% sure this will not fix the issue. I don't think you need 1 kilo ohm. I think 10 kilo ohm is also good. But who knows? Things like that, why I built this board. So here we have 1 kilo ohm. And yep, didn't make a difference. Still doesn't start. Is it connected to E? Yeah, 10 kilo ohm. This is connected there. Let's try the code again. So I²C works. Yep, so it has to do with the initialization that fails. Let's try if the pins are correct. Okay, RS. Where do we use RS? RS PC3. PC3, that's okay. RV PC4. PC4, that's okay. E PC5, is it correct? PC5, yes, that's okay. Then we have pin 4 PC6. Yep. Pin 4 PC6. Pin 5 PC7, that's okay. Then we have PD2. I think I did everything on one port. Maybe that changes something. That's PD2. That's PD3. That's okay. This seems correct. And all the other ones are not connected, but they're pulled up internally. Do I do something? Here. I do something here. This is not what this hard-coded thing should not be here. Yep, that's why it doesn't work. Do I do some hard-coded things somewhere else? Set IO according to nibble. Oh yes. I do. Okay, I need to redesign the board. Or to change the code, but it would be ugly if I change the code. I can change the code so it's a bit more flexible. It uses a tiny bit more CPU. Yeah, because here I do everything on PC. You see here I also set, when I write the nibble, I set PC. I should do the pins individually and write the nibbles individually. It will take more CPU cycles, but we are at 8 megahertz. I don't think this is really important. This will add a huge delay. It will make 2 comparisons every time. This was an optimization So I use only on one port, but this is not the case right here. Okay. So I need to fix this code. I do have some template for setting the direction. Yeah, this is how to set the direction, and I need to set it on these bits. Let's copy one of them, and I think it will be the same for the other ones. Data direction. Do I do something? No, this is here. I only do on right nibble. Okay, it's not a lot of code. It's called, which is called often, but it's not too much code. We need to switch it to inputs. So we do it this way. Switch data pins to inputs. We only use pin 7 to 4. Yep. Six, 4, 5. What is weights are ID input data register? Okay. 6. Yep. 6. This is not only one instruction. These are 2 instructions, because at least 2 instructions, if not 3 instructions better. Meh. Set to outputs. This is where we do it the other way around. Up. This is port. This is specific to port definition, optimized here for speed. I write it in the code. So no optimization, not a matter. I think I could do rerouting, but I think this optimization is not worth the effort. This code optimization, we are running at 8 MHz. Plenty fine, this is not the bottleneck. And we have a typo here. This should be 4. Output, 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 output. And now we write the nibble. This is where I need to change. If nibble and 01. Oh, it's only on nibble, so I don't need to write the full hex, although it will be stored as a byte. Then we need to set the pin, I think. And this is OGR, not this. Port output data register, and I think this sets it high. According to nibble. Oh, why? Okay, this is reverse alert to match pins. This is why I have the lookup table, but now I don't need it. Reverse bit order. Okay, I don't need it because I'm doing, so this is yet another optimization, which I don't need because I will do it for the 4 bits, 4 bits. That's the nibble. Else we clear the bits. And is it really data bit 7? I think it should be data bit 4 because it's the first nibble. Yeah, I think it's 4. I will have to read the datasheet. I will just guess it. 1, 2, 3, 4. It's only 4 bits. 2, 4, and 8. Now we need to change the bits. This is 4 or 5. 5. Ah, damn it. It's not all 5. 6, 6, 7, 7, 7, 7, 6, 6, 5, 5, and we don't need set IO to nibble. That should do it. That did something. Ah, we did write DNA the bit before. But we didn't write any data. Let's check where we did enable delete. Ah, we did pass the init. So we do pass this. This is good. Why don't we write? Ah, is this nibble thing the other way around? Or did I miss something? Write instruction. The address is not set. I need to clear. There's something which is homing this. Write instruction. This returns to home. Let's use this instruction. Let's home, and maybe it's just not using the right instruction or not writing in the right location. I don't remember which location you need to write in. But it does write something. Should still write something. Write instruction. Yeah, it does write 2 nibbles, one at a time. So what is this? This is normally display on, right? Display on, yeah. Display on, that's okay. Then we have, I think it does display on from beginning on. Return home. Return home. Write data. We can check how it does write the data using the command lines. Line 1, yeah. Write data. Yeah, I have an instruction especially for that. So if I don't use the right data, it will not write the data. H. Write data. And it's not write the address. Ah, almost there. Do I want... Normally return home should put it at the right address. Let's try to put it in line 1 or line 0. That's the first data. Go to line 1. Display's on, so that should be fine. Ah, we didn't set the contrast. Maybe the contrast is just all wrong. Ah, and you're also watching the wrong camera. You want to watch this camera. Let's set the contrast. This is not the right screwdriver. This is the right one. Yes, this was the issue. We see an E. Why don't we see the H at the beginning and only the E in the contrast? The contrast is not ideal. Now the contrast looks nice. Hello, let's write hello world. Hello, and then go to line 2. This is this instruction. And then we will write world. Yank past world. Okay. Now it writes nothing. And I don't think this is a contrast issue now. We set the contrast correctly. Maybe the initialization. No. It did write something. Am I not writing the right thingy? Was the E just coincidence? I don't know. Write instruction, set address, that should be fine. Go to line 1. This doesn't clear the display, this clears display. And normally in the init I do clear the display. Where is the init? Here, init. Display on. I already turned the display on. Return home, I already also do it. And I set 2 lines. Yeah, so I don't need to return home and to display on. This is done at the beginning. Because I wanted that you could write the I²C command directly. Oh, I see something. It's blinking. That means that there is something wrong with the data. It's not, the contrast is not too good. Okay, this is the, it really depends on the angle. Oh yes, that I missed it. Also depends on the angle which you're looking at. Are the data bits just flipped? This is possible. Let's just flip the data bits. Maybe that's all. Eight, 4, 2, 1. Yeah, it's even worse. It does something. Does it do it too fast? No, the wait dV or PV nanoseconds. Yeah, we don't wait. These are nanoseconds. I don't have to wait before I latch the data. Do I need to? Let's put one instruction to have this wait. I don't think this is the case. No, that wasn't. That's not the issue. Never had issue with that. 8, 4, 2, 1. I need to read it. Okay. It's in a fucked up state. I should clear the screen before. That would be a good idea. No, I don't know. There is a clear screen. Command. It is in it. This clear display. This one. Let's start with clearing the display. I think I don't do it in my instructions. Here display. Ah, and I could test again if 10K works, but I think 10K will work. There is something wrong with the data. It does try to do something. Yeah. Someone wrote up. Okay, I don't have too long, but it is, why is this, we're at 5 volts, right? This is 5 volts, this is 5 volts. There's clearly something wrong with the data, with setting the data. Did I do some other optimization somewhere? Let me check. No, here there's no optimization. Here it's done correctly. It's one bit after the other. This is right nibble, right instructions. I just need to find PC, for example. Here, PC, nibble, read nibble. The nibble is wrong. This is now how to read the nibble. This is probably why I also don't respect the timing correctly. Nibble. For that I need to read the IDR. If it's this way. But I want the data. Where are the data pins? This way. Still don't know what the pinout is. If and let me check in the data sheets. Data sheets. Hitachi. Hitachi. That was the one. What is? I think this is. Yeah. I think the nibble is one after another. Where is the 4-bit mode? In 4-bit mode, where is it described? Instruction. 4-bit mode is not described here. Timing must be described somewhere. I think, yeah. So this is the data, and this is the instructions. This is in 8-bit mode. Set RAM, set DRAM, blah blah blah. Dots. We don't care. Interface 4-bit MPU. Exactly. This is what I need, and we need the 4-bit because what was this? This is weird. Data bit 7 is the one which is to know when everything is empty. Do I read it correctly actually? And write nibble. Here, read nibble. That's read. I can have also not read nibble, but yeah, I think I use read nibble to wait for the signal to be empty, and I could do it tiny bit faster by not reading all the bits. So, it doesn't, okay. Doesn't tell. This is the lines. Come on, 4-bit mode. 4-bit mode has 8-bit can transfer. Otherwise, 1-bit transfers must be into operation. In this case, time sequence. Yeah, I think it's this way. Bit 7. So it means that this equal 0x8. And we need to do the same with the other ones. 7, 6, 4, 5. Yeah, so what I wanted to do is, yeah, but I think it doesn't matter too much. 6, 5, 4, 4, 5, 6, 7. This is bit 4, bit 2, and bit 1. And we don't need this way. And now we flash. And everything will... it's better. We have LOL. This is a tiny bit better. I think we don't need this. It's not a lot better, but it is a tiny bit better. Hello, well, yeah, yep. I think there's something wrong with the timing. Do I want to insert some knobs here? I don't think that's that. It's just I don't know exactly here where I could continue. That's not it. So am I missing something? Read bytes, that's okay. We need one nibble and then we read the other nibble. What's this? Read busy flag AC. I don't remember what it is. Return byte. Yeah. Set low for instructions and then return byte. Yeah, I think this is the busy flag. And I have some code which does busy waits. Write instructions. Write data. Okay. No, I don't actually. Don't I? I should have code. Normally I do have code which does the wait before reading and writing. Write bytes. Oh, this is wrong. I return the nibble directly. I don't return the lookup table. And there we have it. That's it. It works. You see, it is fast enough and it works perfectly. This is nice. This is nice. I can remove the lookup table. I save. Not a lot of bytes. It's not caught up. It's not really super optimal. How many bytes did I save? 16 bytes. Ooh. Maybe the code I wrote is, but yeah, previously we were at 1.5K. We have 8K, so we have plenty of space. Now we are at 1.7K. The code which writes the individual nibble just takes code and takes time. I could optimize the board layout, but I don't need to. The code is fast enough. But I'm wondering, don't I have? So I can remove this because I'm sure we don't need that. Yeah, we don't need that. That works. I didn't test I²C. We'll test I²C afterwards. So this works. What did I want to do? Yeah, read nibble. This we don't need to do some knobs now because this takes already longer than the ISM. We don't need to wait this on this time. Reading registers takes longer. Yep. Read byte. Don't I wait? I thought I did write the code so it waits before reading between bytes. Why don't I do it? Switch. Ah, here it is. When I write instruction, I wait until the data is ready. So I do it correctly. And I set the busy flag. This is why my code is super fast also, because I just read busy flag all the time and I don't put on the timing. So I do this correctly. So it works. Now I just want to test with the I²C. And there we will use this. I need another cable. I can switch this off. Female, female. Yep. Up, opens. Then I need also to expand the code so it actually reads this data bits to set the address correctly. That's for later. Here. So ACM0, I think I have a picocom. Yes, welcome to the bus voodoo. This sounds nice. MI²C, 100 kilohertz, that's okay. Address 7, open drain. We have external pull-up resistors. We don't need the internal ones. Here we have the pinout. Here we have the pinout on the screen. On the gadget, never completed. So we have ground, and then just need data and clock because VCC is already on the board thanks to the other one. So we have camera shaking. Ground. Which one is which one? Data is yellow. Yellow is data. Ground is going away. Damn it. Up. This way. Now, how do the actions work? I think it's a start condition. Then I 0x47 write. This is to select it. And then I set the address. I think it's, which one is it? I write to, the 0 is in it, line 1. So we write a 1. And then we write in French, coucou. And let's see if it works. And then stop condition. And it doesn't. Ah, command not recognized. Separated by space, available actions. Select slave with I²C address to write. Okay. Read value, white milliseconds. Maybe I just to write once this way. Command not recognized. Can I only write stand start stop condition? That's okay. Can I only write 1 bit? 1 byte? No, that's not it. Let's wait. 47. Command not recognized. Oh. I know. This was correct. It's just that I need to tell it that this is an action. And slave. Select slave. Error. Select slave to write. Error. So the slave has not been selected. Is SDA and SCL correct? SDA yellow, yellow. SDA. It's the wrong pin. Up. That's these pins. Sorry, it's these pins. Now I can start again. Error still. Debugging. SCL is orange. SCL is orange. We don't need to pull up because this is pulled up. And we said it's an external pull-up. Yeah, we have external pull-ups here. Why don't you select? Normally I can write to any address. I can set the I²C address as being any address. This is still 47, right? Maybe if I do it, I'm afraid that when I do a scan it doesn't work. Let's help. Scan, it will block, I'm sure. No, okay, 0. 47. Okay. So 47 does exist. So why can't I write to it? Okay, it does. I don't know why it didn't work before. But it works. See? Coucou. That's hello in French. I have no idea. I think it's this. I think this I²C is broken, but we see that the I²C here works. And myself on line 2. You see how, is it myself? Yeah, myself. You see how easy it is to write now? Just say light run, why to write this text. And the project works. Two projects working today. This is really nice. So, yeah, I don't need a lot of fixes. Just some SIL screening fix, but I will only do it. I will write it in the changelog to change the will I do it myself? Yeah, I need to test if 10k exist work is good enough. And I also, that's for later. But yeah, so this board exists. I can start publishing it maybe. I'll still write that I can make this smaller so I can make this tiny bit bigger. But else, everything works. The code is ready. I just need to put it in Git and to have write commits and so on. But the code, no, the last thing is reading the data bits. Yeah, that's just reading GPIOs. And there's nothing wrong. This is nothing which is really interesting. But that's it for today. Yep, we did 2 projects. USB AC and this I²C to HD44780 adapter. They both work. I'm really happy with tiny improvements. But yep, that's it for the stream. There will be a stream, I don't know when. It's either Sunday or on Monday about the next gadgets. But for today it is finished and you can enjoy the weekends. Bye bye.